Hi, my name is Aniruddha Mukherjee, and today I'm going to be talking about the Murray scheduler, which is a deep learning scheduler implemented in clusters. So first, we will come to the introduction. Currently, deep learning is a very powerful technique in computer science and machine learning, and it is being used in lots of different applications. And as deep learning gets used in more applications, the deep learning models get more complicated, and training the models become more resource intensive, and training the models also uses more time. So usually when a deep learning model is being trained in a cluster, there are multiple resources of that cluster that are being used, namely the CPU, GPU, storage I/O, and network I/O of that cluster are used. And within one cluster, there could be multiple CPUs, multiple GPUs, multiple storage I/Os, and multiple network I/Os. So now we come to the motivation of why Murray is needed. And before we go to the motivation, Murray stands for multi-resource interleaving. But yeah, in the motivation, um, currently the deep learning schedulers are not very efficient in terms of how they use their resources. So a lot of times, uh, jobs that are being trained in a cluster will just sit idly while they wait for a resource or while they wait for another job to finish using a resource. And that idle time period is basically inefficient when we're training very large models or we are deploying lots of jobs in one cluster. So to better visualize this notion, here is a graph. So in this graph, the top graph represents, so the y-axis represents four separate jobs. So A is one job, B is one job, C is one job, and D is one job. And a lot of times schedulers will give, say, job A a certain amount of resources, and job B won't be able to execute until job A finishes executing. Um, but that is a very inefficient use of our resources. So we want something to be represented like in the graph below, where while job A is using the storage resource of a cluster, job B could be using the CPU resource of the cluster. And when job A finishes using the storage resource, job B could start using some other resource. So to better get a grasp of the different components of Murray, we first need to define the resource profiler of Murray, which measures how much each job uses each type of resource and how well different groups of jobs can share resources. Then we must define the job scheduler, which assigns the jobs in the queue to the machines in the cluster. And finally, we have the worker monitor, which keeps track of the resources status of each machine and the progress of each job. So now we will move on to quantifying by what we mean by jobs being idle. So as you can see in this graph, while if we have four jobs, say job A, B, C, and D, and we pair job A and B in one group and job C and D in another group, in these first time periods, when job A is using the CPU, job B could be using the GPU, and when job A finishes using the CPU, job B can start using the CPU, and job A can start using the GPU. But rather, if we would pair job A and C to be in a group, then we would have C waiting for job A to finish using the CPU after C finishes using its GPU for one time period. So over here, after C finishes using its CPU, there is a idle time period that job C has to wait until job A finishes using the CPU. So to better quantify this mathematically, we define gamma, which is the fraction of time that the resources are not idle. And there are some computation examples with gamma. But now we will move on to how we can find the best groupings within a graph. And so we can think of each job as its own node in a graph, and we can create edges to every other node from each node. And then from this graph, we can compute the gamma value for each edge. So once we compute the gamma value, we want to find the pair of nodes that have the highest efficiency or the highest value for gamma. So in this example, A and B can be in one group as the edge weight between A and B is 1, and C and D is in another group because the edge weight between C and D is 1. And we don't want to put C and B in one group because then A and D, well, never mind. So C and B could be in another group and A and D could be in another group. That would be the same, but we don't want to put A and C in one group and B and D in one group because that would not be the maximum value for gamma. And finally, we come to similar visualization to what I showed you guys earlier, where we want to come to a situation where we find the most efficient use of the cluster's resources given the number of jobs. So when one job is using one resource, another job can start using another resource. And approximately when each job finishes using a resource, they switch for the other resources that they need to use to train the deep learning model. And here is the algorithm for MIRI. So in this algorithm, the first few lines basically creates the graph that I showed, and then it proceeds to use the Blossom algorithm to first find a group pairing between two nodes, and then it groups those two nodes into one node, and then the entire search space decreases by one node. And then it proceeds to find another group pairing between that node and every other node in the graph until we find the most optimal value of groups for gamma. But so I think more than explaining the algorithm, it'd be more worthwhile to show the code. So over here, there is an open source link to the MIRI algorithm. It is on GitHub. Now, to compile this code, you would need access to a cluster and the compilation of this code. If you go on the README, it takes, so if you go on simulator and then README, as you can see, it takes about 2 days to 4 days to a day. So it takes quite a while to compile the open source code provided by MIRI. So I created my own MIRI simulator that basically emulates how MIRI is run. So I can show over here. So if you go to sim and then MIRI.py and Visual Studio Code, yeah. So let me make this bigger. So first I have some initial global variables, but after that I have a class called MIRI implementation, which takes a lot of attributes, namely the attributes are the resource type, the job type, and the model type. And under the format.txt, there is a brief description of what each text file should contain. So the resource text files should have a resource name and the number of resources available in a cluster. The job text file should have the job name, which is a unique identifier for each job. And the job name is a string value. And the batch size of that job, the number of batches of that job, the number of epochs in that job, if the job needs to use the CPU, if it needs to use the GPU if it needs to use the storage and all the other resources. And then we have the model text file, which basically creates an estimate of how long one observation of particular job will take in each of the resources. So let's say we have job A and we have the GPU. So the mod.txt file basically creates a summary of how long one observation from the dataset that job A uses will take to make a forward pass in the GPU and a backward pass, or anything to train any individual step it takes to train the model. So then we go to compiling the code. So there are many ways of compiling the code, but first let me show the baseline comparison. So this class is the Muri implementation class, and then after this we have the standard scheduler, which is implemented in most clusters. So this class will be used as a comparison to how well the Muri scheduler is able to allocate resources among the number of jobs. So if we do Python Muri.py and then so over here, first it begins with the standard standard scheduler. First it gives the resources available to the scheduler. Then it gives a brief detail of the jobs that are in the scheduler. Then it gives a brief detail of the total compilation time of each individual job if the other jobs were not present. And finally, we have the total computation time, or this is the estimate. This total computation time is the estimate of how long the standard scheduler's allocation of resources and jobs would take to actually train the entire model. And notice that it doesn't have any units imprinted because the units are actually coming from the initial estimates that we are giving it through the text files. So if we say that the text file units are seconds, then this number would also be in seconds. But if we go over here, we can see that the Muri also outputs a similar result. And along with all the other initial outputs of the Muri outputs, it also outputs a priority queue because the Muri algorithm uses a priority queue to allocate the resources of its jobs and avoid HOL blocking. And in this simple example, basically the number of resources is so limited that the Muri algorithm does not have any room to show its potential. But if I have 13 other, or I have 11 other examples that you can test for yourself. And if I do that, yeah, or so it's easier to see. Yeah. So over here, we can see that in the second example, the standard scheduler took 550 units of time versus the Muri algorithm took 440. So the difference was that the number of resources available to both schedulers had increased, but the Muri algorithm was able to better allocate the resources and overall decrease the number of execution time for all the jobs in that cluster. And finally, I would like to go over some of the results of doing this. So to show the power of Muri, First, I created a simple experiment where I keep the number of identical jobs. So each environment has 5 identical jobs, and environment 1 has the most limited number of resources, and environment 6 has the most number of resources available. So environment 6 has 6 GPUs, 6 CPUs, versus environment 1 only has 1 GPU and 1 CPU. And the number of jobs, and each job performs the same deep learning model training, so they're identical in every way. So these graphs basically represent the execution time for each of the algorithms. So as we can see that the Muri algorithm is able to actually make use of the increased number of resources and actually decrease the execution time. And after a certain amount of resources to jobs, it basically becomes asymptotic. And at that point, increasing the number of resources for the fixed number of jobs would not make the algorithm any faster. But on the other hand, the standard scheduler in this example, and the example was designed in such a way that the standard scheduler would break and would not be able to improve its execution time due to its algorithm, which I have detailed in the report. And as we can see in this experiment, that the standard scheduler does not, in fact, make use of the extra resources, and it takes the same amount of time to compile or complete each of the job training. Next, I created a second experiment similar to the first experiment, but in this instance, I kept the number of resources constant and increased the number of jobs as the environments increased. So environment 7 only has 2 jobs, but environment 12 has 7 jobs. And everything else about the environment was the same, so each environment had the same number of resources to work with. And as we can see from this output, that the Muri algorithm is able to keep a steady, or is able to use the available resources strategically to not increase its execution time as the number of jobs increased. Of course, after a fixed number of jobs, the Muri algorithm started to increase its execution time, but the standard scheduler started to increase its execution time for each environment starting from the very first environment. So the Muri algorithm actually outperforms the standard scheduler in this example. So as a few closing remarks, I would like to say thank you so much for teaching computer networks this semester. It's been a great pleasure, and thank you so much for listening through to my brief explanation for this project. And I hope you have a very good rest of your summer break.